One thing that we have seen so far is how to so we first introduced this notion of random variables, right? And then we discussed two types of random variables, right? There were categorical random variables and what we call continuous or numeric, right? And then for each random variable, we looked at situation where you have only one possibility, one variable. So, for example, so essentially one attribute and multiple attributes. Right? And the same thing with continuous. You could have a single variable, one attribute, or a vector of attributes. Right? So we looked at all of these. Then we introduced this notion of distribution, because wherever there is a random variable, it needs to be generated by some process, and that process is called it's mathematically it's denoted as a distribution, right? So we looked at probabilistic distributions, and then I listed out many, right? And depending on what kind of random variable you have, you would have a different distribution, right? So, for example, in particular we looked at Bernoulli distribution, which is used if you have a random variable which can take two values, right? Like a toss of a coin. However, if you go from Bernoulli to, if instead of a coin you have a dice, then your distribution becomes a multi-Bernoulli distribution. So that's a very simple extension of Bernoulli, right? So instead of having one probability, you have a vector of possibilities. So that's Bernoulli, and then we looked at one distribution which came into the discussion because we were talking about a prior for the parameter associated with Bernoulli distribution, right? So every Bernoulli distribution is associated with this theta, which is the probability of observing heads or one of the classes, right, or success. Then when we were looking at the learning part, we said, okay, we can come up with a bit, not discussion, beta distribution, which has two parameters, a and b. Sometimes we call them alpha and beta, whatever, but they are two numbers, right? And what we saw was that Bernoulli distribution and beta distribution are conjugates of each other, right? So we looked at that, and then I briefly discussed Gaussian distribution, and we will do that in more detail today. So that is third type of distribution that we will look at. But then there are many more, right? And even in Gaussian distribution, there are two types. One is a univariate Gaussian, where your random variable is just one single number, or a multivariate Gaussian in which you have a vector of numbers, right? So that is the second thing that we looked at. The third thing we looked at was concept learning, right? We said, okay, if I give you some training data, can you estimate the parameters of the distribution that generated that data, right? So in machine learning, we call it concept learning or Bayesian concept learning. In statistics, we usually call it parameter estimation. So this is equivalent to parameter estimation, parameter learning, right? So I give you some training data, and then I say, hey, can you estimate the parameters of the distribution that generated that data? So we have looked at that as well, right? We have looked at it from Bernoulli distribution, right? Today we are going to look at it from the Gaussian distribution perspective, right? So at the end of this class, you would know how to do Bayesian concept learning with Bernoulli and with Gaussian. So that after that, what I would expect is that you would be able to do a similar concept learning for any type of distribution, right? Because after this, we would have covered categorical random variables as well as continuous. So tomorrow, if I say, hey, instead of Gaussian, let's say the data is coming from a beta distribution or a uniform distribution, gamma distribution, then you should be able to sort of estimate the parameters for that, right? And in the concept learning, we looked at multiple ways to do the learning, right? So we looked at what is called uh, uh, MLE, right? Maximum likelihood estimation, where you compute the likelihood of your data given the parameters, and then you maximize it to do that, right? We have seen that for Bernoulli. Today we are going to look at it from Gaussian. We have looked at MAP, which is maximum posteriori estimate, in which you combine the prior and the posterior, you combine the prior and the likelihood of the data, and then you compute a posterior distribution over your parameters and use that, right? And then an extension of that is what we call a Bayesian averaging approach, where instead of just taking the parameter that gives the maximum posterior, you use the entire distribution in a Bayesian setting. All right. So we have looked at this from Bernoulli. Today we are going to look at it from Gaussian. All right. So that's number 3. Number 4 was then classifiers. Right. So once we are able to do this concept learning, how do we use this to build classifiers? Right. So we have looked at one which is called naive Bayes classification or naive Bayes classifier, NBC. Right, which essentially makes certain simplifying assumptions and then builds a classifier which can give you the probability of class to be 1 or one of the classes given your training data, and probability for it to be the other class given training data. So that's sort of the basic step of a classifier, right? So it can give you these two probabilities, and using that you would know, okay, which class is it more likely to be, right? So that is the notion of classification, and we have looked at one classifier, naive Bayes, and then today we are going to look at another classifier which is called discriminant analysis. All right. So naive Bayes classifier we looked at in context of categorical data, right, in which your attributes. So you could have one attribute or you could have multiple attributes, right? But they're all categorical. They could only take 2 or 3 or 4 values. However, discriminant analysis is done when your data is a vector of continuous random variables. All right. So this is what we are going to look at today. This and this. Parameter estimation for Gaussian distribution, that's number 1, and then discriminant analysis for continuous variables. All right, any questions so far? So at the end of this, you would have this is still very small part of probabilistic machine learning, right? But you would have looked at these generative models and these classifiers, and you would know how to set up a classifier. In fact, what you could do once you do this, right, you could go back and pull out your hand digit recognition data set, and you can actually build a discriminant analysis classifier to work with that data as well. All right. All right, so now let's start with our Gaussian distribution. Okay, any questions so far? Okay, so what is a Gaussian distribution? We have looked at it earlier, right? The main thing that you want to remember about a Gaussian distribution is, and we are going to look at it in 2 ways. So first is your random variable x is univariate. Whenever I say univariate, that means it's a single number, right? It's not a vector, it's a single number, right? So let's say, so it could be, so some of the samples that can come out of this random variable could be 0.7, 3.4, 5, 4.2, things like that, right? So that's the univariate distribution. If we assume that if x is generated by a Gaussian distribution, right? And sometimes just to keep it simple, we say if x is Gaussian, right? Which essentially means if x, the random variable x, was generated by a Gaussian distribution, then the probability density, and we are going to talk about probability density now because these are all continuous values, right? So we cannot say the probability of x to be 5. That won't hold because there are infinite possibilities. That means we'll say the probability density at x, some value of x, is given by 1 over underscore 2 pi, right, sigma square exp minus half x minus mu whole square sigma square, right? So that is a very standard expression. I hope most of you know about it already, right? But that's the probability density for a Gaussian random variable, right? So what you see here is that there are two parameters associated with this random variable. Sorry, yeah. Sorry, it's 2 pi sigma, right? I just want to make sure my notations are all uh, right. Oh, sorry, sigma square. All right. Yeah. So this is outside this under root sigma square. So that's a probability density, right? And now, so there are two parameters associated with this distribution. There is a mu and a sigma. Of course, pi is a constant. So these are the parameters. Just like in a beta distribution, you had a and b. In a Bernoulli distribution, you had theta. In this case, you have mu and sigma, right? And I told you last class, what do these mean, right? This basically the shape of this probability distribution, the density function is a bell curve, right? And the point at which the curve is highest, that's the sigma, that is determined by mu, and the width of this curve is determined by sigma, right? So that is that. Now we can extend it and say if x is multivariate, right? Or if x is a vector. So instead of one value, it is like, let's say, three values, 0.7, 0.2, 0.1. So every sample of x is a three-dimensional vector with three values, right? In that case, uh, we talk about this distribution p of x, which is given by, which has a very similar shape, except now instead of having parameters which are these scalar numbers, you have vectors and matrices, okay? So in that case, it becomes determinant of this matrix raised to d by 2 exp minus half right. So now it essentially has very similar form as this one, except that now your parameters are not scalar anymore. This is a vector, so this is a d cross 1 vector, and here is a d cross d matrix, right? Typically we call that the mean vector, and this is called the covariance matrix. All right. So the density at any value of x is now given by this expression. All right. So it has similar shape, but of course, given that now your parameters are both uh, vector and matrix, they become slightly different. Any questions so far? All right. Just give me a second. What is written just after raised to d by 2? Yeah. So this is so I assume that you remember your matrix calculus and matrix algebra classes. So this is the determinant of this matrix, right? Raised to power d by 2. All right. Okay. So now how do we do Bayesian concept learning here, right? So Bayesian concept learning means that I give you some data. All right. I give you some data points, and now you want to find out the parameters of the Gaussian distribution that generated this data. All right. So we are going to do it directly for the case of vector random variables, which means that d is not 1, right? So you can think of this, right, this single variable distribution as a special form of this, right? So if you set d to 1, it exactly becomes this, right? Because if d is 1, then this is a 1 cross 1 matrix, which is essentially a number, right? In which case this just becomes 1 over sigma square, and then uh, this determinant just becomes the value of the absolute value of sigma, right? So it's exactly uh, what it means. So actually, one thing I should say is that typically we say that mu sigma square are the parameters, right? Okay. So now we are going to look at how to do Bayesian concept learning, which means that I'm giving you some x's, right? Some vector x1, x2, x3, xn, right? And these are all, let's say, and d is fixed, of course, right? So let's say d is 5, then these will all be 5-dimensional vectors with values in them. And now you have to find the mu, which will be a 5 cross 1 vector, and a sigma, which is a 5 cross 5 matrix. So how do we do that, right? So the answer is pretty simple. So we can first apply the maximum likelihood estimation procedure, right? So according to maximum likelihood procedure, what we need to do is first compute the likelihood of the data set. So this is our data set, D, right? So if this is our data set, we first compute the likelihood, and usually we call it L, right, of D, and then maximize with respect to mu and sigma. All right, and typically, if you remember our discussion earlier, see, likelihood is just a product of all probabilities, right? To make it mathematically more easier to compute, we deal with log likelihoods, which is the same thing, except that the products become sums. So we will actually compute the log likelihood, we'll call it LL of D, and we'll maximize that, and whatever value we get, that is the maximum likelihood estimate of mu and sigma. All right? Any questions so far? So this is more statistics than machine learning, right? But the reason I want to go in detail here is that in future you might use some other distribution in your whatever you're doing in your research or work, and you need to follow similar procedure there as well. All right, so it's a nice exercise to go over this, and some of the mathematical notations are all given in the handout. So if you miss writing something, don't worry about it, right? So let's do this part. Okay. So the first thing we will do is we will say, okay, how to compute the log likelihood. So log likelihood of the data set is given as log of the probability density at each data point. All right, which is given as, now remember, it is given as log of the product. Now this is a product sign from I equal to 1 through n. These are all the data points you have. The probability density at xi given mu comma sigma. Right, so you're computing the probability density at each data point, and then you're taking the product of this. That will give you the likelihood, and then you're taking a log of it. That gives you the log likelihood. So because of the log, this becomes a sum. Right, and then you can compute this. We know what this expression is. This expression is what I wrote here, right? So this is essentially this expression. So I'm going to write it like that. So we are taking log of these two things. So these both are getting multiplied. So that becomes minus log of under root 2 pi, right? And log of exp, both things disappear, so it's 1 minus 2 x minus mu transpose, so x of I. All right, any questions so far? So that's how the expression becomes when you expand it. All right, and then we can break these two. So remember, there's nothing that depends on I here, right? So we can keep it outside, and that just becomes minus n, because this whole thing can be taken out of the summation, and that summation just sums up to n log of root 2 pi, and I'm going to break this as well, minus n log of determinant raised to d by 2 minus half summation I equal to 1 through n x of I minus mu transpose minus mu. All right. Now remember, we are going to differentiate this because we want to compute the value of mu and sigma for which this thing is maximized, right? So if you look at it, this part is a constant, so we can ignore that, right? So we will just say that my LL is same as, I mean, it's not equal to, but we don't have to keep these values because they won't, when you take the derivative, these will disappear, right? So I'm going to take it off, is equal to minus n by 2, because this log of something becomes d by 2, right? N d by 2 log of, sorry, log of this, right? Minus half uh, all right. I'm a little confused. I think I wrote this expression a little. It's actually, this part is 2 pi raised to d, and this is just half. Sorry about that. Which means that here, this is just half, okay? And this is nd log. But since this disappears, right? So we just write n by 2 log of this thing minus half of this. Is that right? Log of this, oh, I see, will be half, right? There's a minus sign here, and there has to be a minus sign here. I think I need more coffee. All right. Uh, happening here? Somewhere I went wrong. I'm trying to backtrack without changing too much. Okay. Well, I'm going to skip a couple of steps because I think I confused you more than I intended to. But essentially what it comes out to is that the log likelihood, right, can be written as n by 2 log of determinant of the inverse minus half the summation this x of I minus mu transpose sigma inverse. So these two are two different. This is a sigma, this is a summation x of I minus mu. All right. So now what we do is now we have to maximize this with respect to sigma and with respect to mu. Right. So let's do first. So maximizing with respect to mu. Right. So what we will do is we will compute the partial derivative of this likelihood with respect to mu, and then we will set it to 0, right? So this would be, now remember this term does not have mu, so this will go away, right? So this term will come out to minus half summation I equal to 1 through n d by d mu of x of I minus mu transpose minus mu. All right. Now this is an expression which is sort of not quite what we have seen before, right? Because this mu is a vector. All right. This quantity is going to be a scalar if you think about it, right? So these two will give you a d cross 1 vector, and the transpose of that is 1 cross d. This is a d cross d matrix. This is a d cross 1. So if you multiply all of these, you'll get a number, right? That's called a quadratic product. So we want to differentiate a number with respect to a vector, and you will get a vector out of that, right? We have seen that before. Now, how do we do that, right? How do we compute this derivative? And that's actually fairly easy if you refer to the matrix cookbook. All right, so let me introduce this very fascinating resource that I suggest all of you download on your computer, which is called the matrix cookbook. So if you search on internet, and it's also there on Piazza, but it's a fairly detailed resource, 72 pages, which essentially has a lot of results related to matrices and vectors, right? So if you need to compute derivatives of things, right? So derivatives of matrices, vectors, products of vectors and matrices, inverses, right? Everything is here, right? If you want to look at derivatives of things with respect to a vector or with respect to a matrix, right? So there are all these results here. So this is not what you need for your for this course much. We might use a few results from here, but in future, whenever you want to compute these kinds of intricate matrix derivatives and vector derivatives, you can refer to this resource, right? So I'm going to not go through the process of deriving all of these. If you look at the handouts, part 2 handouts, right? This has all the steps here, so you can follow those. Right, so it's fairly easy. I mean, easy once you sort of follow the steps. So what I've shown you in the class is how to reach till computing the expressing the likelihood, right? Log likelihood like this, and then what you do is you essentially compute the derivative of this log likelihood with respect to mu and sigma. Okay, and in that what we do is we use these results from the matrix cookbook. So they're not really magic results, right? That's what it is. They have just put it in a nice form, and then you just set it to 0, and then you compute the estimates. All right. So the thing that I want you to focus on today is what we get. So this is the MLE, the maximum likelihood estimate of mu, when you set this to 0. All right. So if you look at it, it comes to 1 over n summation all x's. So it's essentially the sample mean, which makes sense, right? So if I give you 20 numbers and I ask you to compute the expected value, right? The easy thing to do is just take a mean of it. And even by the maximum likelihood estimate, you get the same thing. So you see one pattern, just as what we observed in the Bernoulli distribution as well, is that maximum likelihood estimates for the maximum likelihood estimate kind of follows common sense, right? Even in the Bernoulli distribution, by doing all of that, maximizing the probability and setting it to 0, we got the estimates, which were essentially the number of heads divided by total number of trials, right? In the same way, even here, the MLE estimate makes common sense. It is essentially uh, the sample mean of the data set that you have. And then if you do the derivation with respect to the sigma, right, if you want to find the best sigma, the expression for that comes out to this. And that also makes sense. This is the sample covariance. If I give you a data set and ask you to compute the covariance, right? So you can compute this, right? You first compute the sample mean and then you compute the covariance, right? So that covariance is the MLE estimate for the covariance matrix as well, right? So that is one point I want to make. And then we move to slightly more complicated derivations, which we won't do, but still want to show it to you, right? So what we did today was we were able to see how to derive these two expressions. Right? We didn't quite go through the steps, but you can follow the notes. But essentially what you get is that the MLE estimate for the mean vector is just the sample mean of your training data, right? And the MLE estimate of the covariance matrix is the sample covariance matrix, all right? So that is that. But the second thing, just as we did in the Bernoulli case, was how do you incorporate some prior, right? This is coming just from the training data. But what if you want to incorporate some prior as well, right? What if somebody tells you that the prior estimate of the mean is something, right? And this is giving you the MLE estimate and you want to combine it, right? So the procedure is still the same. You multiply the prior with the likelihood to get the posterior, right? And then you maximize that. However, it turns out that as we saw in the Bernoulli case, the mathematics becomes easier if you use a prior which is a conjugate of this distribution, right? So if your distribution of x is Bernoulli, then we saw that a prior on the parameters of the Bernoulli distribution can be set to beta, because beta and Bernoulli are conjugates of each other. In the case of Gaussian distribution, it turns out that for the mean, because there are two parameters here now, right? In Bernoulli, we just had one. In case of Gaussian, in the mean, right, the prior for this distribution is actually a Gaussian distribution itself, right? So the prior distribution for mu is a Gaussian distribution. It's a conjugate for the, so Gaussian is a conjugate of itself. That's how it works. And for sigma, the conjugate is an inverse Wishart, right? That's a separate distribution. I don't know if you know about it, but inverse Wishart is a distribution that is defined for matrices, right? So we have looked at Gaussian, right? A univariate Gaussian distribution, the sample is a number, right? A multivariate Gaussian, a sample is a vector. Now, if you want to generate matrices as your samples, right, then also you have a lot of distribution. So there's a distribution called Wishart, which generates matrices, and there is a distribution called inverse Wishart, which also generates matrices. So it turns out that if you want to set a prior on your sigma, you can use an inverse Wishart distribution. All right. So we won't go into all of this math. Basically, the idea here is that you compute, you have the PDF, the probability density function for your priors, right? This is the normal distribution, and this is the inverse Wishart, and then you can multiply it with your likelihood and get the posterior. However, what you get once you compute the posterior, is that the posterior distribution for your mu is also a normal distribution, which makes sense because both of them were conjugates of each other, right? So you started with some prior distribution of mu, which was this. And then you looked at your training data and you computed your posterior distribution for mu, which also looks like a normal distribution whose mean is this and variance is this. So this is something that I don't know you will need for this course, but you just need to keep in mind, because in later phases of your life you might come across these things as well. Any questions so far? All right, good. So what we have done so far is we have looked at how to do Bayesian concept learning for here. Is we have seen how to do Bayesian concept learning in Gaussian distribution. All right. Now we are going to use this knowledge to build a classifier when your data is continuous. All right. And we kind of looked at it in the last class as well. Is here. So remember the naive-Bayes classifier, right? The naive-Bayes classifier said that you can compute the probability of your class given your data. Your data was a vector of certain attributes, right? So in this example, your data had 3 attributes, and then each one of them was binary. But what if each one of them is a number? It's a continuous number. You can still apply the same naive-Bayes philosophy, except that now your probabilities will not be modeled as Bernoulli distributions. They will be modeled as Gaussian distributions, right? So again, the probability of y given x. So let's say y is your class, right? Let's follow a similar example. Let's say your class is malignant or benign. The probability, the posterior probability of y to be malignant given this is your training data. Now this x is no longer a vector of binary attributes, but a vector of continuous attributes, can be written as this. This comes from the naive Bayes assumption, right? We are assuming that your x, each component in x is independent of each other given their class label, which means that you can factorize it like this, and then each one of them can be modeled as a distribution which is a Gaussian distribution, right? So then you can write it like this. Okay, so let's write it in a little more detail. So let's say your x, right? X is basically 3-dimensional vector, right? So this could be, let's say, this could be the size in meters to 0.5 or centimeters. This could be the weight in milligrams to 30, and this could be the some position value, so 7, right? So these could be 3 different attributes. So this is how your data is expressed as. So now what you want to do is, what is the probability of y to be malignant given x is some x star, right? So this can be written as, assuming that each one of them is independent of each other, is probability of y to be malignant. Well, we first write it in sort of the Bayes rule way. So this would be given as x equal to x star given y equal to malignant times y equal to malignant divided by that denominator that we usually see, which is the sum of these things, right? So now this, right, this can be factorized because this we are assuming is they are all independent of each other. That means that we can write this as probability of x1, which is the first component, to be whatever x1 star given y is malignant times x2 equal to x2 star times malignant, right? Now since we are modeling each one of them as a normal distribution, right, or Gaussian distribution, you can write it as, I'm first going to write it as a product I equal to 1 through whatever d or 3, and this is p x I equal to x I star given y equal to malignant, right? And then each one of them is a Gaussian, so it can be written as 1 over 2 pi sigma I exp minus half right. That's because we know that is the value, right? And then what happens is and then so for each attribute, right, each individual attribute, there is a sigma I and there is a mu I, right? So you can think of the parameters of this distribution as 3 pairs of values. So you will have a sigma 1 mu 1, you have a mu 1 sigma 1, mu 2 sigma 2, and mu 3 sigma 3, because there are 3 attributes, right? So you want to learn this. Once you have this, then you can compute this probability. All right. So then the next thing that we observe is that if you have this product, right, this product can also be written as this value. And that is where I'll stop today, and maybe we'll do more next time, is that this product here can actually be written as a multivariate Gaussian distribution. So if you create a diagonal matrix, right? So a diagonal matrix has all zeros in the off diagonal entry, but the diagonal entries, if you replace those with these sigma 1 square, sigma 2 square till sigma d square, and you create a mu vector, which is essentially the mu's associated with each attribute, then that product can be written as this, right? So in some sense, what you're assuming is that even though you said that each example, right, each attribute is independent of everything else, and each attribute is modeled as a Gaussian distribution, univariate Gaussian. But when you compute this, it essentially means what you're assuming is that your entire X is modeled as a vector, okay, as a d-dimensional vector. So it's modeled as a d-dimensional multivariate Gaussian, right, with mu as the whole vector, but the sigma is special. Now your sigma is only a diagonal matrix which with values on the diagonal. Okay, so that's sort of a special case of a general multivariate normal, right? In a general multivariate normal, sigma could be anything, right? However, in this case, sigma is diagonal. So that's essentially what you're doing. You're treating your X as a multivariate Gaussian with zero covariance. Covariance, when you say covariance, it means that the variance across the off diagonal terms are zero, but the variance, there is some variance on the diagonal terms, right? So that is what we call a discriminant analysis, right? So after that, so once you compute this, right? So now you can compute the probability density for X at considering the class is 1 or malignant and class is benign as this. And once you compute that, you can now compute the posterior for the thing that I was trying to write earlier, and then whichever is higher gives you the right class, right? So this is sort of the equation for a Gaussian discriminant analysis. So in next class I'll go through the steps of how do you learn these things, right? However, if you want to, the one thing that you want to is that Gaussian discriminant analysis has a very similar form as naive-Bayes classifier, except that the only thing that has changed now is that instead of having Bernoulli distributions here, now you have replaced it with a normal distribution. All right? Any questions so far? Yes. Yeah. Right. You mean together? So the question is that here what I showed you when we were setting the prior, right? We were setting a prior on the mean separately and the sigma separately, which meant that when we were computing the posterior for mu actually depended on the sigma, and the posterior for sigma depended on, well, that didn't depend on me. But so there is some dependence, right? But so what you were asking was, what if we can set a prior on both together? But that's mathematically it's a little challenging. That is what you want to do, but mathematically it's challenging because they both have different forms, right? One is a matrix, one is a vector. So what we end up doing is we're kind of approximating. We're saying, okay, let's set independent priors on both of them and then compute the posterior. Right? Question? What is the what? In this equation over here? Oh no. That I wrote here? This one? This is a transpose. See, what you're doing is your x is a vector, right? So x minus mu transpose, that gives you a 1 by d thing and multiplied by this. Right? Any other questions? Yes. Right. So when you're trying to do the classification, right? So if you remember, you want this, the probability of y to be 1 given x, and you break it down using Bayes rule as this. So this is essentially p of x given y equal to 1.
Then what is how do you get to p of y?
Can you repeat that?
How do you get the probability of y?
This part?
Yeah.
This is just the prior on y. So this kind of follows, see, y is still a binary attribute, right? Y is your class label. And we model that as a Bernoulli distribution. So we use just, this is exactly what we did in Bayes, naive Bayes as well. All right?